All right. We can start. 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 All right, sorry for that disturbance. Okay, now begin. Okay, so today we are going to look at yet another very important lesson, which is electrical energy and capacitance. Electrical energy and capacitance. I'm sure this is not the first time you are hearing the term electrical energy, or it's not the first time you are actually hearing the term capacitance. So we are going to look in details, and this is actually on slide number 2, which is on Moodle. You can easily get that on Moodle. All right, so first of all, we want to look at what is called work. I'm sure you've heard about it, and we're just trying to recall on some of the things that you have done at high school, as well as some of the things that you could have even looked at in the first semester. So, of course, when we talk about work, what are we talking about here? So we are saying the amount of work that is done. For example, the work may be in form of potential energy. The work may be in form of kinetic energy. The work may now be in form of the change in the initial and the final energies. For example, work may be defined as the potential energy, which is initial, then the difference with the potential energy, which is at the final state, that gives us minus the change in the potential energy. For example, if this is our surface, it means that what it means is that we have that. What it means is that if this is our surface, then we have this is our body, which is at a certain height, and this height we call it h. So it's fine. Okay, so that means we are saying that the potential energy, which we all know as, this height, then multiplied by the gravity, multiplied by the mass. This one has a mass, which we are calling m. Then we also have the height from the ground to where the body is, which we are calling h, like that. Then we also have the g, which is the F due to gravity. In most cases, this value are going to be given in the exam, which is 9.8 meters per second squared. All right, so what we have is that this potential energy now will read as mgh, like that. So there is the potential energy. Let's take, for instance, this is at point A, that is at point B. So what we have is that at point A, that's where we have the potential energy, which is initial. Then, assuming this body is coming down or is dropping to the ground, then we have point B, which gives us the final potential energy. And in order for us to actually get the work done, what we have is that we should find the change in the potential energies, which is nothing but mgh. All right. Okay. So that having been said, we move on to what is called work and potential energy. So how do we combine the two? Like we mentioned when we started, we said this work is actually the difference in the potential energies. In other words, that's why you were given even at high school an example to say if we are moving some object on the same surface, so we see to it that actually the work done, we are saying if you are moving on a straight surface, but which you cannot find in reality, the work done may be zero. So whatever you are carrying, assuming you are moving on a straight surface, so the work done is assumed to be actually zero, but in reality you never find the straight surface. That's why even if you are carrying something that is so light, after some time you feel the pain or you feel the weight of that item that you're carrying. All right. Okay, we move on. So let's look at the potential energy in form of the terminals of the battery, like we mentioned last week. So in a cell, for example, we have this arrangement where we have the positive terminal and the negative terminal. So what is there is that in order for us to complete this circuit, we need to connect these two terminals. For example, you have a bulb here. Now, what is happening is that as long as this circuit is not complete, of course you have your switch somewhere here. As long as the circuit is not complete, what we see is that there will be no electricity that is going to be passing in this circuit. But what makes the current to pass in here is that there is a point with high potential and all right, and the other one has low potential. And the difference in the potential is what brings about the movement of electrons from one point to the next. So that is the way it is. Now, what happens is that the moment we have this difference in the potential, that means there is work that has to be done in order to move electrons from one point to the next. And that is why there is what we call work and potential energy. In other words, we need some amount of energy to move electrons from one terminal of the battery to the other terminal. And in the end, what we see is that there is some movement of electrons, hence we have electricity in the circuit, and the bulb may go on. But now, there is an amount of energy that is actually needed to move these electrons. So in order for electrons to move in the circuit, there is energy that is needed. And that is what is called the potential. And this is the potential which is measured in terms of what? In terms of voltage. That's why when you see a battery, it's written on top here either 1 or 1.5 volts. So that is the potential that you see on the battery. All right. Okay. Now we move on to what is called electrical potential. Right. So this electric potential is actually the change in electrical potential energy. This is how you define it. So this is the change in the electrical potential energy. And how do we put it in mathematical terms? We are saying the change in the potential energy must be equal to the negative, of course. I will explain why we have that negative, because it is actually opposing the left-hand side. So we have the negative, then we have our charge, and so we have our negative charge. That negative is just there to show the direction. For example, you have the electrons are moving in this direction, but the current opposes the direction of the electrons in the circuit. So that is why we have that negative in front there. So what we are saying is that this is negative multiplied by ED. All right. So here, what we see is that if we have a particle of charge Q in a field with a strength E over a distance D, so that depends on the charge of the particle. So here, this D is the distance. Then this is our electric field. Then that is our charge. So that gives you the change in the potential energy. All right. So let's look at an example. An example, we are saying a particle that is Q1 All right. I hope it's a bit clear. Let me try to close the window. I don't know how that is. Can you confirm? Is it a bit clear now? Let's confirm if the board is clear. I'm seeing some comments that the board is not too clear. Okay, thanks for the response. Then we can continue. Okay, I was saying, let us look at a simple example. We have been asked to say a particle Q1 with a charge which is plus 4.5 microcoulomb is fixed in space. So we are saying let's collect our data first of all, which is very important. We have a particle which is Q1. This particle has plus 4.5 microcoulombs in terms of charge, is fixed in space. And that is from a distance. So we have this particle, which is here, which we are calling Q1. Then it is actually fixed in space from a distance of 3.7 centimeters. So we have a distance of 3.7 centimeters, a particle Q2 of mass 6.9 grams. So we have another particle which is here, which is our Q2, and the distance from here up to there is 3.70 centimeters. Then we are saying this has mass 6 points. So the mass, which is M2, is 6.9 grams. All right. So that is, then of course, the charge here has been given to be minus 3.10 microcoulombs. So here we are saying from a distance, we are saying a particle Q1, which is this one here, is with a charge 4.5 microcoulomb is fixed in a space. From a distance, of course, the distance we have put it there, which is 3.70, and then this Q2 is given to be of mass 6.9 grams, and that is the charge that has been given. So we are saying from a distance of 3.70 centimeters, a particle Q2 of mass 6.9 grams and charge minus 3.1 microcoulomb is fired with initial velocity of 60 meters per second. So here, this is the charge, but the V1, V2 is equal to 60 meters per second. Then towards the fixed charge. So in other words, this charge is actually fired in this direction at this speed towards Q1. So Q2, this one is stationary here. And then we are firing a charge Q2 in this direction at this speed, 60 meters per second. This has mass 6.9 grams. Then we have the charge of minus 3. Now, what is its velocity when it is 1 centimeter away from Q1? Let's say it is somewhere here. This is where Q1 is. And this distance is nothing but 1 centimeter away from Q2. So, when you find such a question, for example, in an exam, you shouldn't even panic. First of all, try by all means to understand what the question is asking you to do. The first thing the question is telling us is that there's Q1, which is placed in a space. We are given a space, and Q1 is placed here. Now, the second thing is that at a distance of 3.7 centimeters, we have Q2, which we are actually firing at the speed of 60 meters per second. Now, this Q2 has a mass of 6.9 grams. Then it has a charge of minus 3.1. And Q1, of course, has a charge of 4.5. So what should come into your mind is this. This Q1, let me put it here so that it's a little bit clear on the other side. Okay. So what we are saying is that this Q1 is actually positive. That is very important, and that must tick this. Then the other one, which is here, is actually negative. So what will happen from the start? We said, unlike charges do what? They attract in that way. So this is our Q2. And this distance now has reduced to 1 centimeter. And the question is asking us to say, what is the velocity when it is 1 centimeter away from Q1? So first of all, what we need to actually understand here is that the change in the kinetic energy plus the change in the potential energy. So this is how you start your solution. I'll show you how to proceed. But in the end, you should be able to actually get to the final answer. What is important is that when you are starting your solution, the first thing that should come into your mind is that this energy is actually conserved. So when energy is conserved, what it means is that the change in the potential energy plus the change in the kinetic energy must be equal to 0. That is a must. It must be equal to 0. So what is the change in the potential energy? The change in the potential energy is the change in the potential energy. We are talking about Q1, which is actually stationary. That is the potential energy. The change in the kinetic energy, we are talking about once a stationary Q2 now in motion, and that must be able to give us what? Must be able to give us 0. And now what we are looking for is this, which is the change. We know that the potential energy of this at this particular time, it is 0 because you have mgh. Assuming it is on the surface and h is equal to 0, this gives us 0. So what we have here is our half mv squared in terms of change. So you have half, that is, say, m1a, which is m2 here. You have m2 v2, which is the initial, of course, okay, say the final, minus half m2 initial v2 initial squared. So this is the difference we are looking for. Then we have been asked, remember there is a 60, which is this one here. This 60 is our initial velocity, which you are going to come and place here, which is this one here. That is our initial velocity. The velocity at which we are hitting this charge towards Q1. So that is our 60. You've been given this. What else don't we have? We've been given the mass. This mass is the same as this other mass that we have. The mass of this charge will not change. Whether at this point, at 3.7 centimeters or at 1 centimeter, the mass remains the same. What else don't we have? What we don't have is what is this one here. This is where you put your question mark, because you don't know the velocity. You've been asked to say, what is its velocity when it is 1 centimeter away from Q2? This is what you are looking for. So the question appears too complicated, but it is very simple. From here, you make V2 the subject of the formula. And then you equate the rest. The rest of this goes on the right side. And then what next? Do your simple maths. We don't mark mathematics, we mark the physics. So do your simple mathematics, just replace the numbers there after making V2 final the subject of the formula, and then you are done with your calculation. I'll repeat that. So what is important is for you to understand that from the conservation of energy, this is what we have. The change in potential energy plus the change in the kinetic energy must always give you 0. But this potential energy, we are looking at the potential energy of Q1, which is stationary. And assuming it is on the surface where we are starting to be our ground, which is 0, then this potential energy gives us what? Gives us 0. And then we now deal with the kinetic energy. Since at one point, this had some potential energy, which has now been moved into kinetic energy. So there's kinetic energy at a start, at that velocity, and now we've been asked to find when it is 1 centimeter away from Q2, what will be its final velocity. So you do the initial, the final minus the initial. You have the initial velocity, you have the mass. You have the mass, but you don't have the final velocity. And then you make V final, V2 final, the subject of the formula, and you calculate this so well without any problems. In other words, the potential energy here has decreased because initially it was at rest, but now it is in motion. The potential energy has decreased, but the kinetic energy has actually increased. So it's that simple. So moving forward, we look at the next part, which is what is called capacitance. Okay. All right. Of course, you've done this before. When we talk about a capacitor, this is just a simple apparatus that is able to store charge. What is the simplest way of putting up a capacitor? You have it as two plates in that way. Then, of course, assuming this is positively charged, then that is negatively charged, then separated by a distance d. This is how simple you structure a capacitor in that way. So now, we are saying the potential difference if you are given such a device, which is the capacitor. So this one actually is a device that is there to create a constant electric field. Now, the potential difference here, which we are saying, the potential difference in this case, which is of course the V, must be equal to the electric field, which we normally abbreviate as E, multiplied by D, which is the distance between the two plates. This is, of course, a plate, positively charged, and then you have a negative charged plate here. Now, for us to find the voltage across this capacitor is nothing but the electric field that it produces multiplied by the distance between the two plates. And we have our potential difference. Okay, so we are saying, what about the charge that is stored here? Because we have agreed to say the capacitor actually stores charge. Now, how do we calculate that charge which is stored by a capacitor? In simple terms, we have the potential difference, which is the electric field multiplied by the distance. But now, the charge which we have now, if you are talking about the charge that is stored, which we normally write as capital Q, is nothing but equal to the capacitance of this capacitor multiplied by the potential difference, which is V, as simple as that. So you should be able to know how to manipulate these formulas, given that V is equal to ED, and then Q charge is equal to CV. So you can easily bring this down here, which is the same as CED, like that. Or you can simply say capacitance is nothing but charge over what? Over potential difference. As simple as that. Okay, let's move on to its relation now. Let's move on to capacitance and understand how the area of a capacitor actually affects capacitance. Okay, now we have this capacitor here which has a certain area. This area has a potential to affect the capacitance of a capacitor. What is the capacitance of a capacitor? Capacitance is defined as the charge divided by the potential. In other words, the capacitance of a capacitor is defined as the amount of charge that a capacitor is able to store in a given space, so to say. Now, in an event that we have the area here, our capacitor, which is C, our capacitance, is equal to, or we can say is directly proportional to the area of the capacitor divided by the distance. Right? This is how you put it. So we are saying the bigger the area, that is the surface area of the plate, because on top here, this plate may be like this. So the bigger the area, the better the capacitance. But the shorter the distance, the less the capacitance. So this is the difference. But now, when you want now to put in an equal sign here, the implication is that the capacitance must be equal to a certain constant of proportionality, then multiplied by A divided by what? By D, where this is the area, that is the area of the plates, like that. Then this is the distance between the plates, and that is the constant of proportionality, which is called the permittivity. Okay, and that constant, of course, you will be given in the exam, and it's 8.85 times 10 to the minus 12 F, which is the Faraday, of course, per meter. And of course, A is nothing but the area of the plates. All right. Okay, I think that we have already discussed. Okay, let's look at capacitors in parallel. How do we connect capacitors in parallel? Okay. All right, let's put a simple circuit here. All right. Now, what we have is this arrangement. First, let's say this is our C1, this is C2, this is C3. Then that means, remember where we are coming from. We mentioned that the charge is equal to capacitance multiplied by the potential. Now, in this case, what we have is that C is nothing but charge over what? Charge over potential. So in this case, what will be our Q1 here? This becomes our Q2, then that is our Q3. So we want to calculate first for Q1. Of course, we have some voltages, a voltage source somewhere. Then what we have is that Q1 must be equal to C1 multiplied by V. Then, of course, Q2 must be equal to C2V. Then Q3 must be equal to C3V in that way. Now, in this case, we want now to find the equivalent capacitance. How do we do that? We want to find the total capacitance in our case. Let's say, in fact, what is there is we are going to remove this, the last one, just remain with 2. Then this we can put as our battery source. So we can just put that as our terminal, which is our V, down here for the sake of right. Then what next? We want to say, okay, what is our C equivalent? So C equivalent must be equal to C1 plus C2, which is this multiplied by that. I mean this plus this. C1 plus C2. This is what we are looking for. If you've been asked to say your capacitors have been connected in parallel, let's say you have capacitor 1 and capacitor 2, how do you get the equivalent capacitance? This is what you do, as simple as it looks. So in an event that we had C3, C4, C5 going in that way, what you do, you just bring it here, C3 plus all the way up to a number of capacitors that you actually have in your circuit. Now, we know that, of course, this Q equivalent also is the same as Q1 plus Q2 plus Q3 plus, you add them in that manner as the number of capacitors. Now, in order for us to find the capacitance, the total capacitance for these two, of course, this is the simplest that you can ever have. At times, you may be given 3 or 4 of them, so that you've been asked to say you find the total capacitance. So that is how you get the equivalent capacitance, putting in mind that actually this Q is nothing but CV, but CV is Q over what? Over V. So let's look at this and simplify it in that way. So we know that C1 must be equal to Q1 over V, and C2 must be equal to Q2 over V. That means C equivalent, which is C1 plus C2, must be equal to Q1 plus Q2 over V in that way. And that gives you the capacitance. All right. Let's look at capacitors in series this time around. Okay, let me just check some of the comments. All right, this is in series. In this case, what we have is that we have, of course, our battery source there. Then we have C1, C2, And of course, we have this arrangement, C1, Q1, C2, Q2. This is our voltage connected in series. Of course, we know that the voltage here will have V1 here over V2, because now it is in series, the voltage is not the same. So here, what we have is that 1 over C equivalent will be equal to 1 over C1 plus 1 over C2. That is how you calculate the total capacitance in series. But remember, in parallel, it is calculated in this way. So don't confuse the two. This is the opposite of the voltages. Here, you realize that V will be equal to V1 plus V2 in this case. But if capacitors are connected in series, it means that 1 over C equivalent must be equal to 1 over C1 plus 1 over C2. If they are connected in parallel, C equivalent is C1 plus C2 straight away. That is the difference. Okay. Let's look at an example. Okay, we'll look at a simple example there. All right. So we are saying, given 3 capacitors of 1 nanofarad, that is, a capacitor can be constructed that has minimally a capacitance of what? So we have been told we are given 3. So that is our data. We have C1, which is 1 nanofarad, C2, and C3. So the question is asking you to say, at times, this question may not always appear under multiple choice. At times, you may be asked, even in section B, to say, you have been given some capacitors, then you are asked to say, show how you can connect this so that the total capacitance is equal to a given figure. So a figure may be given to you to say you have been given 4 capacitors. Now you should come up with a diagram in order to come up with the C equivalent, which will be as per question. So here the question is asking us to say, given 3 capacitors of the same size, how are you going to connect them in a way that they give you the minimum capacitance that you actually need, right? All right. Now, how do you do that? Straight away, you know that, of course, 1 over C equivalent is nothing but, of course, we have 1 over C equivalent, because you know for sure, if you just go straight and add them like this, you have the maximum. So you use the other formula, not that one. This is the same as 1 over C1 plus 1 over C2 plus 1 over C3. Of course, that gives you straight away 1 plus 1 plus 1, which is 3. And then we know that this gives you 1 plus 1 plus 1, which gives you 3. Then C equivalent becomes 1 over 3. That is nanofarad. As simple as that. So this is what you do given such a very simple question. Okay. All right. So let me give you a practical situation. I will just show you a tactic that you normally use, especially in an exam situation. So if you find in an exam, for example, you have such an arrangement, for example, you have this arrangement, then of course that is our power source. Let's say this is C1, C2, C3, C4, C5. Then you've been asked to say you should actually find the equivalent C. How do you do that? So the first step is for you to reduce this component, which is here. You know that these are connected in parallel. So you know which formula you're supposed to use when you are connecting those in parallel. So your next diagram straight away from here becomes this. That is our voltage, like the one that we have there. Then this becomes your C. Of course, that is 1, 2, 3. This becomes your C4. This becomes your C5. So from here, straight away, you can combine these. You know that when they are connected in series, you know how to add them straight away. So from here, you know that this will be your arrangement in this way. Then you have your C1, 2, 3, C4, 5. Then now you can combine these in parallel, which you can now move to this one. This is your voltage. Then this becomes your C1, 2, 3, 4, 5. That is the easiest way you would do it in an exam situation. This one is so easy and it makes sure that you don't make mistakes. So first of all, you reduce your circuit into small components and not forgetting to check whether what you're combining is either in parallel or in series. Then from there now you start reducing your circuit until it becomes as small as that. Then that way you'll be able to actually solve your problem so well without a lot of problems. Okay. Okay, let's move on to what is called the energy. Of course, that is stored in a capacitor, which is the work done, of course. Okay, so in a capacitor, we know that we have the positive charge and we have the negative charges. This is our distance, which is d. Then, in order for us to store charge here, it means that there has to be movement of charge from this point to this point, trying to attract each other. But the challenge is here, there's a gap. So there should be an amount of work that must be done in order for us to achieve that. So that amount of work is actually the difference in the potential, the change in the potential multiplied by the actual charge that you have. So when you have the change in work, so the change in work gives us the potential multiplied by the change in the charge. So here, the work done, which is the change in the work done, must be equal to the potential difference, which is the voltage, the difference between the terminals multiplied by the change in the charge of the capacitor. So that is the amount of energy that is actually stored in a capacitor. So at times you may be asked as part of the question to say determine the amount of energy that is stored in a given capacitor. So when you have the voltage, for example, the voltage source, which is this one, then you have the change in the charge that gives you the change in the work done. So we are saying the work done in transferring a small amount of charge, which is a small charge, dq, from a negative to a positive, that takes an amount of work equal to the change in work, which is equal to the potential difference multiplied by the change in the charge. All right. Let's look at what is called the charge density. Of course, this one we've seen it before. I'll just define it and move on. All right. So charge density the charge density, normally we actually abbreviate it as rho this way, which is the charge density is the amount of charge that is passing through a given area in a specified time. So we are saying the amount of charge per unit area is what is called charge density. So charge density is nothing but the amount of charge per unit area. That means charge per unit area. You are done. Don't even waste time telling stories. Charge density is nothing but the amount of charge per unit area, which is that sigma is equal to charge over area. And the units, of course, is coulomb per meter squared. In that way. Okay. Now, if you recall very well, from here we had an equation of capacitance, which is the same as sigma multiplied by, of course, the area over the distance. That is what we had as capacitance. Now, how do we combine these two? We know that what is common here is the area. So immediately we can actually, from here, you know that the area must be equal to charge over what? Over sigma. So that, of course, becomes this. We are multiplying by the area, which is charge over sigma, all this multiplied by 1 over d, which is nothing but that sigma comes to this other side. Then you have your d, which we are dividing here. Like, for example, at this is what we have, A over d, which is nothing but charge over rho divided by d, which you can put in simple terms. For some of us who are not too good in mathematics, you can say charge over rho, this is divided by d, which is q over sigma multiplied by, of course, 1 over d. That way, multiplied by 1 over d if you want. Then you can make C the subject in terms of sigma and charge. You can combine the two equations depending on the question, what the question is looking for. Because at times you may be asked to find the charge density, but you could have, what you've been given is the capacitance, and you've been asked to find the charge density. So you need to know how to actually find the relationship between charge density and capacitance. We know that charge density is equal to charge over area, capacitance is equal to epsilon 0 multiplied by area over d. So from there now, the question may give you the capacitance, but you've been asked to find that. It will be very difficult for you if you cannot see the relationship here. And you would say, because you go on the first page and check the equations, you will not see an equation that is going to combine this and that, because we expect you to do that. Okay. Okay, I think we'll end here for today. We'll continue next week. Wish you well and enjoy the rest of the day. Please find time to go through the questions. And if you have any question concerning the tutorial sheets, please ask. We are able to assist you in whichever way we can. We know it's online, but we can still assist you. All right. Okay. Wish you all the best and enjoy the rest of the day. Bye-bye.